hopefully that will not mess up. Try something here first. Let's start out with customary. Are there any questions? Yes, Ty.
Could you do one example of momentum where the two forces are coming at 90 degrees again? Like,
Like the cars colliding?
well, like it's like there's clocks moving from the north, clock moving to the east, and then they collide. Yeah.
Okay. The big thing, it's a two-dimensional problem. So let's just make that 10 kilograms traveling at 15 meters per second, and this one 20 kilograms traveling at say 5 meters per second. If they collide in a closed environment. Now, in reality, there's interaction with the road, there's other things going on, there's sound, heat generation, and so forth. So it's not exactly a closed system, but we will pretend that it's a closed system so that there's no other influence other than these two objects going to hit each other. So let's just start out with the magnitude. Well, first off, what is the formula for momentum?
Mass times velocity.
Yep. You were is that what you were saying? All right. So what's the velocity here? That way? Some might say to the right. But of course, we physicists, we don't want to write to the right. So how do we get away with not having to write all those words? So we just say that's I hat direction. So the velocity here is 15 meters per second I hat. And so the momentum, m sub 1, or p sub 1. What is the momentum of it then?
150.
Generally, you put the I hat at the end. If you put it next, that is not inherently wrong, but just untraditional.
Newton seconds.
Yeah.
So,
Newton
sorry.
seconds.
Newtons, I'm good with that. That didn't, or kilogram meters per second. Or make up your own unit. All right, what about this one? What's its velocity?
5 meters per second.
All right. So for two dimensions, you basically establish perpendicular directions like that. So what is its initial P2?
100 seconds J.
All right. So therefore, what is the initial momentum of the system?
Newtons per second. I had plus
Say 150 what?
and we will put it in there. I said Newton seconds.
Okay, you said per second. Newton seconds, I hat.
I had plus 100 Newton seconds J.
All right, there you go. If all you're trying to find is what is the initial momentum, done.
For this problem in master set, I tried to do it through like if I'm going through like I tried to find result and like C squared equal to A squared.
Okay,
Does it make sense?
yeah, alright,
Because-
so let's,
because-
so it depends on, if the question is, what's the momentum, done. Momentum's a vector, we got directions in there, this is my initial momentum. You don't have to go any farther than this. If the question is, what's the magnitude of the momentum, then we're gonna have to use Pythagorean theorem.
I believe.
Sorry, were you? Wasn't sure if you're talking to yourself or,
I will, loosely, in the mastering set, you have to find both.
let's see. This relates to chapter 6.
Yeah. Chapter 6, problem 4. I can just give you the numbers. Since I have the-
I just don't have the question, I have the answer though. All right, so, yeah, I asked for the initial momentum or final momentum. I asked for the momentum, so, and not the magnitude.
What is the magnitude of the final velocity of the combined graph?
Okay, that's part B. All right, so part A, we have this. I believe it's a perfectly inelastic collision.
Doesn't say. Oh, they're going to collide and stick together.
Okay, so perfectly inelastic collision, they collide and stick together. What's my final momentum, by the way? We solve for initial, how do we, if I wanna know what final velocity, I need to know my final momentum.
Same as initial.
Say it again?
Same as initial.
Yes, momentum's conserved. In physics, conserved means whatever you start with, you have the same at the end. So that's also P final. And that should be, since they stick together, it's now, I can treat it as one object, it's the mass final times the velocity final. What's my, in this problem, what's my final mass?
30 kilograms.
I hope so. All right, so they stick together, so this is 30 times my final velocity. All right, so the math problem we're working with here is basically my final momentum is equal to mass times velocity. Mass final times velocity final. We have 150 Newton seconds I hat plus 100 Newton seconds J hat is equal to 30 kilograms times V final. If I'm trying to solve for V final, what do I need to do? So on the right-hand side, I've got my final velocity. On the left-hand side, recognize I'm dividing the whole thing by 30, which only means I'm dividing this by 30 and this by 30. I've seen way too many students at all sorts of different levels of math who go, oh, 30 goes into 100, goes into that 5 times, and they forget this one completely. So it's 150 divided by 30, which is 5. I hat. Then that looks like a J, so let's try that one again. I. Plus 3.3 J hat. Units?
Meters per second.
Yes. It's a velocity, meters per second. So I can do meters per second. Meters per second. Or 5 I hat plus 3.3 repeating J hat meters per second. If I just want to write it once, I do need the parentheses. All right. But if I want to find my final speed, I have two ways of getting to my final speed. The speed doesn't have direction, it's just the magnitude. I'm adding two vectors here. I got 5 to the right. I got 3.3333 going up. My resultant, from where I begin to where I end, that is my final speed. How do I solve for it?
Pythagorean.
So 5 squared plus 3.3 squared is equal to v squared. And whatever that happens to be. Somewhere around 6. I think.
You got 36.11.
36.11 is v squared.
6.0092.
Meters per second.
There we go. You recognize what did the units look? Alternatively, and I think this gets to something that you were doing, we could have found the magnitude of the momentum because I know the part's right there, so let's just figure out what the magnitude of my momentum is. Well, I'm going to the right 150 and I'm going up 100. So my resultant, from where I begin to where I end, just like all the other additions we've done. So p squared is equal to 150 squared plus 100 squared. P squared is somewhere around 180.
Yeah, 180.28
Units?
meter, Newton seconds.
Okay. So that's the magnitude of my momentum. Because I have just a single object, that's got to be equal to the mass of that object times my final speed. So that's equal to mass times speed, since we're doing magnitudes here. So that's 180.28 is equal to 30 v, and v comes out to somewhere around 36.0092. And it could be a little bit off if you use a calculator, depending on how you round it. Oop. Six, not 36. Okay. I guess, did I answer your question?
I believe so, yeah.
Just not 100% sure.
Yeah, I'm pretty sure. And so, if we're just doing velocity, then our answer is still with the I hats and the J hats, because we
Yep.
need to preserve our direction. That
Correct.
speed solution doesn't have a direction involved, so it's not the velocity. It's the speed.
Right. Right.
I get better word, which is why it's the speed, not the velocity, because it loses the direction.
Correct.
I think that I jumped to try to do the Pythagorean theorem, and then I got confused on how to include the direction. But I didn't need to do the Pythagorean theorem because it was finding the velocity. So I think that's where I got confused.
All right. Other questions on this? Other questions?
I have a question, but it's not about that.
Okay.
Question number 7 on chapter 7. Box is sliding on a flat, frictionless surface until it reaches a spring.
Yep.
What is the maximum that the spring will compress you must trade with?
All right, so it's a question just how to do it.
Basically.
Okay. It's chapter 7, so energy's involved. So cruising along, got a spring. What are the forces involved in this problem?
The normal force and weight.
All right, so I got weight acting down, I got a normal force acting this way. When it hits the spring,
There would be a normal force and weight.
well, we still have those two. You're talking about additional?
Do you mean when it reaches the spring, or
Yeah.
the spring it's just by itself?
No, when it reaches the spring.
There would be a natural. I keep saying natural for some reason. Normal force.
However, in this case, when you're dealing with a spring, we don't call it, yes, it is a normal force, but it's more specifically, it's an elastic force or a spring force. So, and I make that distinction is the fact that this is a conservative force. Now, the normal force and the weight are perpendicular to the movement. How much work are the normal force and weight doing?
0.
Okay. This normal force is a non-conservative force, but it doesn't do any work, so we don't care. This is a conservative force, but it's still not doing any work, so who cares? This is the only thing that's doing work. If I have a conservative force doing work, it's changing energy from one form to another. So it's changing energy from the kinetic into potential. Well, I know my initial energy. Wow, that's probably why it was over there. My initial energy is equal to my final energy because the only thing doing any work is conservative, so energy is conserved. I got kinetic and potential. You know the question's about to come up, so look it up if you have to. U for potential energy, K for kinetic energy. Then move back here so I can hear all the voices equally. All right, here we go. What's the formula for kinetic energy?
1/2 mv squared.
That was nice. Formula for potential energy?
Which one?
The one associated with this spring force. That's the
One,
NGH goes with weight.
1/2 K displacement squared.
Okay, so 1/2 K displacement initial squared. And just the same stuff over here, so except final, MV final, plus 1/2 K delta X final squared. The spring is just hanging there, or just sitting right there. It's in some equilibrium position. We're assuming a frictionless surface, so the spring is, I keep going back to that colleague who kept using the expression fat, dumb, and happy. Spring is just sitting there fat, dumb, and happy. It is an equilibrium to start with. Initially. So the displacement, that delta x, is how far this thing gets either squished or stretched from equilibrium. So this would be delta x equals 0, and then it's going to compress when the box hits it. And so how much it compresses, that is, well, that's going to be my final, and that's my initial. So just based on my description right there, that is 0 because it hasn't deformed. For the pedantics out there, it's because I said so. All right, now, something else is going to be 0. What else is going to be 0 in this?
What is?
Kinetic final.
Yeah.
Sorry?
Because we're stopping the problem when the box stops, that V final is also going to be equal to
Okay.
0.
If you're looking for maximum compression does indeed occur when the box stops. So that's 0 because V final is 0, and this is 0. Right. So the problem just simplifies down into 1/2 mvi squared equals 1/2 k delta xf squared. What is k? It's what?
Exploding states.
Oh, yeah, but what is it? Not looking for a value, looking for the concept. What does k represent?
Spring constant.
Okay, that's a step. All right, so k, spring constant. It's a stiffness constant. So we can just, I'll write stiffness down here. The bigger the number, the harder it is to deform. So if it's 30 newtons per meter, that means it takes 30 newtons to stretch it a meter, or compress it a meter. If it's 50 newtons per meter, it takes 50 newtons to stretch it a meter. So it's a stiffer spring, the bigger that number is. Matter of fact, if it's 30 newtons per meter, it takes 30 newtons to stretch it a meter. It takes 60 newtons to stretch it 2 meters. It takes 90 newtons to stretch it 3 meters, and so on. So the force, ignoring direction. This is the spring constant.